Hi, we are now going to learn about units and dimensions. In physics, measurement is very important. And whenever we measure a quantity, we don't just represent it in terms of numbers. We also have to say in what units. For example, if I were to measure the length of a railway track, I won't just say 1000. I'll have to say the length is 1000 meters. Okay? It's very important to specify in what unit you are measuring. Same way, if you are measuring the velocity of an object, you won't just say it is 10. You will say it is 10 meters per second. Right? So whenever we measure a physical quantity, we talk about the number, the numerical value, as well as the unit. Okay? The measure of a physical quantity always is expressed in terms of number as well as unit. Now, of course, we don't have to only measure it in terms of meters. We can measure it in terms of centimeters. We can measure it in terms of kilometers. So the same physical quantity can have different units. For example, 1000 meters, we could have written it as 1 kilometer, right? So you can represent it in terms of a different unit. The length can be measured in meters or kilometers. Similarly, instead of saying 10 meters per second, you can talk about the unit as kilometers per hour, and you can say that the velocity is 36 kilometers per hour. Okay? And of course, you can always convert from one unit to another as long as you are talking about the same physical quantity. Suppose you want to convert kilometers to meters, that is possible. For example, 5.2 kilometers, you know a kilometer is 1000 meters. So 5.2 into 1000 meters, 5200 meters, right? So you can convert kilometers to meters, but why are you allowed to do that? Because both of these are talking about the same physical quantity, length. On the other hand, if you want to try and convert between different physical quantities, that is not possible. Example, suppose I want to say 3000 meters and I want to express it as so many seconds. Is that going to work? No, because this is in meters, we are talking about length, whereas that we are talking about time, right? So this makes no sense. You cannot convert length into time. They are very different quantities, right? So the nature of the quantities, they have to be the same. Only if you have the same physical quantity, then you can convert between units. Now, a particular physical quantity can have so many different units, right? So sometimes it's a bit confusing. So we talk about dimensions. So because a physical quantity can have many different units, we talk about physical quantities in terms of a unique thing that we call its dimensions. Dimensions basically says that you are trying to represent that physical quantity in terms of something fundamental. For example, if you take speed, there are so many different units for speed. Meters per second, kilometers per hour, feet per minute, right? Now, but if you look at all of these, can you see a pattern? Meters, kilometers, feet, they are all lengths. Whereas, if you look at this per second, per hour, per minute, you're talking about time. So, in all of these cases, you're talking about length by time. So, you can then use that to talk about the dimensions for speed. All these units, you can say they have the same dimensions, length by time, or LT power minus 1. Because it's a by time, you can always take it up there and put the exponent power minus 1. So LT power minus 1 or L by T, right? So all of these, you see, have length by time. Okay? So the units are different, but in terms of length and time as fundamental quantities, we can write all of these as the same dimension L by T. Another example, let us look at another example, density. Now density is mass by volume. So you can think of kilogram per meter cube as one of the units for density. Gram per cc is another common unit, right? What is cc? Cubic centimeters, right? So gram per cc is another way to express the units for density. Pound per liter. Pound per liter, not a very common one, but that's another way to express density. Now, if you look at all of these, kilogram, gram, pound, they are talking about mass. And meter cube, cubic centimeters, liters, volume, that is basically length cube. So you can write the dimensions for density as mass by length cube. m by L cube, which is m L power minus 3. Notice that the units are different, the dimensions are the same. So we are going to focus on dimensions because one physical quantity will have one unique dimension. Okay, let's try and understand this. So whenever we talk about dimensions, remember you are writing it in terms of something fundamental like length and time. So we are going to focus on which are the fundamental dimensions that we are going to use to express everything else in terms of these. Now I want you to remember that the same physical quantity, it can have different units, but it will always have the same dimensions. Okay, and only if the physical quantities have the same dimensions, only then you can convert between the units. So different units, but they must have the same dimensions. Only then you can convert kilogram per meter cube to grams per cc. Similarly, you can convert kilometer per hour to meters per second. That is allowed only if they all have the same dimensions, which they do, right? You can see meter per second and kilometer per hour, both represent speed and both have the same dimensions. So then you can do this conversion. Otherwise, it's not possible to convert. Let us now understand the difference between fundamental physical quantities and derived quantities. To do this, I'm going to start with an example. We know that speed, you can write it in terms of length and time. So for speed, usually we use the symbol V. V for velocity, we're going to use the same symbol for speed. So V is equal to L by T, length by time. Now this relationship connects velocity or speed with length and time, right? So if I consider length and time as fundamental units, then I can use length and time to derive the units for speed, right? So we should not consider this as a fundamental quantity. We should consider this as a derived physical quantity. If length and time are considered fundamental, then speed will be a derived quantity. Now you can argue, wait a minute, why don't I multiply these two and write L is V into T? So why not consider speed and time as fundamental quantities? Absolutely fine, you could do that. Okay, if speed and time are considered as fundamental quantities, then length will be a derived quantity. Does that make sense? Yes, it does make sense because speed of light is a constant. So some people argue that speed should be considered a fundamental quantity. Using that, we can then derive speed and time, we can derive the length, right? So we could have written speed and time as fundamental quantities and use that to figure out length as a derived quantity. But what is important is you cannot say all three, L, T and V, all three are fundamental quantities. You can't do that because if you choose two of these as fundamental, the third one becomes derived. If you chose these two as fundamental, the third one becomes derived. Same way you can say length by V will give you time. So you could have defined length and speed as fundamental quantities and made time as a derived quantity. It doesn't matter which two you choose as fundamental. The third one becomes a derived quantity. So there is a choice in selecting the fundamental quantity. So which are fundamental quantities? If you select a bunch of quantities as fundamental and there is a choice involved there, then everything else in the world you must be able to write in terms of the quantities you have selected as fundamental. So if I chose A, B, C, D, E as fundamental quantities, then F, G, H, everything else I should be able to write in terms of A, B, C, D, E, right? I should be able to express it like this. So then you can say that these are fundamental quantities, but not just that, right? Because none of these you should be able to write it in terms of the others. So you should not be able to write D in terms of A, B, C and D. You should not be able to do this. So if none of these can be written in terms of the others, right? So that means you need all of these and everything else in the world you can write in terms of this. Then this will be called a set of fundamental physical quantities. And there are 9 such fundamental physical quantities in our world. By using these fundamental physical quantities, we can write every other quantity. We can express it in terms of these 9. Now we have a choice of which 9. Right? You already saw that you could have chosen velocity and time as fundamental, or you could have chosen length and time as fundamental. Same way, in these 9, there is a choice. But the International System of Units, which is the accepted system across the world, SI system, it has already made the choice for us. So we are going to follow the SI system. SI system has selected 9 fundamental physical quantities. We are going to stick with those 9, though there was a choice to select a different 9. Okay, but there are 9 fundamental physical quantities using which every other physical quantity in the world can be expressed. Let us now look at the choice that was made by the SI system. Let us now look at the fundamental physical quantities chosen by the SI system. The first quantity is length. The second quantity is mass. The third one is time. We already know the SI units for these 3. Okay, just remember, for mass the SI unit is kilogram, not grams. The fourth fundamental physical quantity chosen by the SI system is current, and the SI unit for that is amperes. Now, if you think about current, how is it defined? The rate at which charge flows, right? So, it is charge divided by time. That is current. Now, current is defined in terms of charge. So, it seems like charge should be defined as the fundamental physical quantity. Actually, if you look inside an atom, electrons have a fundamental charge, protons have a fundamental charge. So, if you look more deeply, it does feel like charge should be a fundamental quantity. But it doesn't matter. If you choose charge as a fundamental quantity, current will be a derived quantity, charge by time. But if we instead choose current as a fundamental quantity, charge will become a derived quantity, current into time. Okay, so you can choose anything as a fundamental quantity. Okay, that is a choice. Keep that in mind. And the SI system has chosen current, not charge, as the fundamental quantity. Of course, why did they choose current? Why didn't they choose charge? That is because in a practical way, you can measure current much more easily than you can measure charge. So they based it on practical considerations on how you measure, and therefore they chose current as the fundamental quantity. And since the SI system is what we all use, once we have selected current as a fundamental quantity, charge automatically becomes a derived quantity. Keep that in mind. Okay. The next fundamental quantity is temperature. The unit for this in SI system is Kelvin. We write it as K, not Celsius, not Fahrenheit, Kelvin. Okay, keep that in mind. Amount of substance is also a fundamental quantity, and we measure it in units of moles. Okay, so for example, in chemistry, we use this a lot. So we ask, how much chlorine? How do we answer? 3 moles of chlorine, right? So amount of substance is measured in moles. We also, of course, use this in physics as well. Then we have one more fundamental quantity called luminous intensity, and this is measured in candela, and the symbol for that is CD. Okay. Now, luminous intensity tells us how bright a light source appears to an average human eye. Okay. Now, remember that here we are talking about human eyes. So, for example, how bright a source appears to a human being, that is what luminous intensity is measuring. It doesn't care about how it appears to dogs or cats or tigers. It focuses on human beings. So, this is very human-centric physical measurement that we do for luminous intensity. There is one more quantity which sometimes people confuse with luminous intensity. Luminous intensity is talking about how bright a light source appears to a human being. Whereas this intensity without any thing in before it, or sometimes you can call it energy intensity or just plain intensity, that is something that is very different. That talks about how much energy flows through a unit area in unit time. So that is basically energy divided by area into time. So energy can be written in terms of length, mass and time. Area is of course length square, and time of course is already a fundamental unit. So energy intensity or just intensity or radiant intensity we can call it, that is very different. That's a derived quantity, whereas luminous intensity is a fundamental quantity. Luminous intensity talks about how bright a source appears to the average human eye, and that is measured in candela. So here you see that I have given you 7 fundamental quantities, but we are talking about 9 fundamental quantities, right? So there are 2 more, and these are angles. One is of course the usual angle. We call this the plane angle. Why plane? Because you either draw this on the notebook or on a board like this, so it's a plane surface. Usually when we talk about this angle, we talk about it in degrees, right? But degrees is not a great measure. So we define this measure in a slightly different way by saying angle theta, okay, is arc length divided by this radius, S by R, arc length by radius. And the unit for this, SI unit for this is radians. We write it in short form as RAD. So plane angles unit is radians. But often we also need to measure what we call solid angle. So for example, when I'm looking at the world around me, I'm seeing this whole angle, right? So like a cone, that is called solid angle. So solid angle, which is this angle, solid angle, it is measured by looking at the area here divided by r square, a by r square. That is the definition of the solid angle. And solid angle is measured in units of steradians. Steradian basically stands for solid radians. Okay, so steradians, and we write it as SR, SR. Okay, so we've got 7 of these, 8 and 9. So these are the 9 fundamental physical quantities, and with all of those fundamental units that you see. Okay, there are 7 fundamental dimensions. Let us now look at these. Now each of these physical quantities comes associated with a dimension. So length, we say, has a dimension L. So for length, we write the dimension L, capital L. For mass, we write the dimension as M. For time, we use capital T to talk about time dimension. For current, we use A. Don't confuse the unit symbol A with this dimension. For both, we are using A. Okay. For current, we use A. Some people use I, but generally many books will use A for current. For temperature, obviously we cannot use T, so we use K. Kelvin is the unit, but here we are using K to talk about the dimension temperature. Amount of substance, we use mole itself, and for luminous intensity, we use CD. Okay, candela is the unit, but here we use CD itself to talk about luminous intensity dimension. SI units, sometimes people talk about luminous intensity, the dimension used for that is J, and for amount of substance instead of mole they use N, but many books will use mole and CD, so we'll continue to use it like this. So we've got 7 of these fundamental dimensions. Wait a minute, what about for these angles? Plane angle is S by R, that is arc length by radius. Arc length is a length, so length by length, the length by length will cancel out, so radians will be dimensionless. Plane angle is dimensionless. Same way, when you look at solid angle, you have area by r square. Area is length square by r square, so length square by length square. Again, that will cancel out. So basically, solid angle will also be dimensionless. So basically, there are 7 fundamental dimensions that we will use because these 2 angles are dimensionless quantities. Okay, because they are plane ratios of length to length, length square to length square. So basically no dimensions for either plane angle or solid angle. Now I just want to make a small point. In the SI system, you have these 7 quantities that have fundamental dimensions. So we'll use all 7. We'll be using all 7, including for amount of substance, we will be using mole. We'll be using mole. Okay. Now SI system says that we must use this with a dimension mole. But some people say mole is just a counting unit. When you say dozen bananas or dozen apples, you don't think of that as something with a dimension. It's just a counting unit. So mole is also a counting unit. So some people feel like you can ignore this dimension for mole. So that is also something that is correct. You can ignore it. But the reason SI system uses it is because that will then put in a discipline that we actually talk about the fact that there is this counting unit that we have used. So we don't make a mistake. So SI system expects that we will use mole whenever necessary as part of the dimension. Okay. But if you ignore it, it is not that you made a big mistake, because all other counting things that we do, right? Any other groups that we use, like a dozen and so on, we will actually say it is dimensionless. We could have treated this also as dimensionless because it is just a counting unit. But in the SI system, it is generally prescribed that you use basically a dimension for mole. So in the SI system, usually they use it as N. N is for Avogadro number. So they use this as N, and they use candela instead of writing it as CD, right? For luminous intensity, they use J. But we will use these 7 fundamental dimensions. Now remember that while there are 7 fundamental dimensions in most problems, you are going to use only these 5. So these are the 5 main dimensions. We'll generally avoid looking at mole or luminous intensity. So we'll not do too many problems using that. But these 5 are going to be super important. Now using these fundamental units and fundamental dimensions, every other physical quantity, its units and its dimensions can be derived. So everything else is derived. Okay. These 9 quantities are fundamental. These 7 dimensions are fundamental. Everything else can be written in terms of these.